Why do we have exponents and radicals? Not that I hear that question a lot, but it's probably one that we've all wondered before. You've also probably heard previous teachers tell you that exponents is just repeated multiplication, but that actually is wrong if you look at the pattern of it. But one explanation is that allows us to move between dimensions. And when we move between the three dimensions that we're used to, we can expand that and imagine different dimensions or see a pattern and extend that pattern further. For instance, if you have one dimension, that's like a point or a line. And if you have two dimensions, this is now area. We put two lines together, or three lines or four lines, and the space in between is our area. And then we have 3D, which is what gives us volume. And we add another dimension, and it's the space inside of this cube. We can turn this into a pyramid. We can turn it into a prism. But in order to go from one dimension to the next, to move up a dimension, you have to use a property of exponents where you have your base to some power, like 1, times your base to another power. And remember, you add those together. I'm really hoping you remember what this oh, I about gave it away there. What this exponent rule is. Since I about slipped, I'll tell you. This is the product rule. We get x squared. And if I want to move up again, x to the second power times x to the first, that's how we get x to the third power. So 1 dimension, 2 dimensions, 3 dimensions. So if I wanted to imagine what something in 4 dimensions would look like, I would take x cubed times x to the first. That would give me x to the fourth. And we can continue this pattern to move higher and higher up. What if I wanted to move down? What if I wanted to find the area from volume? What would I have to do? Now I'm going to use the quotient rule of exponents. And I'm going to take x to the third divided by x to the first. And that's going to give me x squared. And if I want to move down from area to a side length, I'm going to continue to use that rule. It's going to give me x to the first. What if I wanted to imagine a dimension even smaller? Something without any dimensional units? Well, take x to the first divided by x to the first. It's going to give me x to the 0. The 0 property tells me that this is equal to 1. What if I wanted to move into an imaginary, like, first dimension, or like a mirror of a point or a line? You guessed it. We're going to divide x to the 0 by power by x to the first. That'd be 0 minus 1, which gives me x to the negative first. What I like about this is it also shows on this side here that 1 divided by x to the first is equal to x to the negative 1 power. The cool thing is that this pattern works for any base. It doesn't have to be x, and it doesn't have to be just looking at 3D physical shapes. It doesn't have to be looking at area or even lines and points. We can look at anything. Consider a base of B. We are going to look at this for the exponent range of -5 to 5. And we're going to compare that with the range of a base of 2 and 10. So I'm going to set up a data table here, just a quick one. Here's base of B, base 2, and base 10, and I'm going to put X up here to show that those are in fact our bases. If I look at B to the 5th power, that's B times B times B times B times B. If I drop to the 4th power, we drop a B. If we have B to the 3rd, we lose another. 2nd, we have 2 B's. B to the 1st, we just have B. B to the 0, we have 1. B negative 1 is equal to 1 divided by B. B negative 2 is equal to 1 divided by B times B. Negative 3, 1 divided by B times B times B. And we have B to the -4th, 1 divided by B times B times B. Oops. B to the -5th is 1, 2, 3, 4, 5. What do you think is going to change when we move to base 2? Anything? The only thing that changes is what letter is in between, or symbol is in between those multiplication signs. Same thing if we move to a base of 10. These patterns do not change. Radicals, we're going to see a similar pattern there as well. And those are going to serve the purpose of returning any base to the nth power to a base 0. And that's going to help us find the points on a graph where our y value is equal to 0. That sounded super confusing. It sounded way better in my head. Not going to lie. All right, we're going to reimagine. No matter if this is y equals x, y equals x squared y equals x to the third. Okay. I'm going to mark this in blue. Y equals x. Okay. It crosses the line one time. This has one root. If I move to this one, I should have two roots, depending on what's going on. Okay. If this is, ooh, that was no bueno. Actually, that's going to have one root. Minus 3. Now we have two roots. One and two. And then we'll have 3. For this one. To neutralize, I do the root of its opposite. You know, x, it has a power of 1. I'm going to take this to the radical of 1. It doesn't do anything. Don't do that. We're going to skip this. And we're not going to worry about anything greater than or less than that. We're only going to look at square root, cube root, maybe fourth root. Maybe. But these are the two you need to be the most concerned with.